ኦኬ ሰላም እንዴት ናችሁ? ይህ ማትማቲክስ ፎር ዩ ዩቲዩብ ቻናል ነው። በዚህ ቻናል ዛሬ ይዤላችሁ የቀረብኩት የአፕላይድ ማትማቲክስ ቱ ሚድ ኤግዛም ሶሉሽን ነው። ስለዚህ ዛሬ ይህንን የዚህን ፈተና ሶሉሽን በጋራ እናያለን ማለት ነው። ይህ ፈተና የተዘጋጀው በጎንደር ዩኒቨርሲቲ ነው። የተሰጠውም ለጎንደር ዩኒቨርሲቲ ኢንጂነሪንግ ተማሪዎች ነው። እዚህ ጥያቄው ወይም ደግሞ ይሄ ፈተና 6 ጥያቄዎች አሉት። 30 ነው የሚታረመው። ስለዚህ በተቻለ መጠን ሁሉንም ጥያቄዎች ሰፋ ባለ መንገድ ለማየት እንሞክራለን ማለት ነው። ስለሆነም ምናልባት ለዚህ ቻናል አዲስ የሆናችሁ ልጆች ካላችሁ ቻናሉን ሰብስክራይብ እንድታደርጉ እየመከርኩ አሁን ቀጥታ ወደ ጥያቄዎቹ እንሄዳለን ማለት ነው። ስለዚህ ወደ መጀመሪያው ጥያቄ በምንገባበት ጊዜ የመጀመሪያው ጥያቄ ይሄ ነው የሚሆነው። ምንድን ነው የሚለው? ዲተርሚን ዌዘር the sequence that is -1/3 to the power of 1 plus 1 when n is running from 1 to positive infinity is convergent or divergent. That means what we are asking here is we are asking just to determine whether this sequence is convergent or not. So do you remember, or what we must know here is that a given sequence is said to be convergent only when its limit at infinity is existing, and if the limit at infinity simply doesn't exist, so that the sequence is said to be a divergent sequence. So knowing the convergent property of the given sequence is simply the same as determining or simply knowing whether the limit of the given sequence at infinity is existing or not. So let us try to calculate its limit. Know that here the limit of -1/3 to the power of n plus 1 is equal to, we apply laws of this one, that is exponents. There is the limit -1/3 to the power of n times this one, so that we have there is a constant. Therefore, there is equivalent with this one, that is -1/3 multiplied by the limit of -1/3 to the power of n when n is approaching to infinity. But we know that here the limit that's really when n gets larger and larger, the numerator that is -1 or simply here becomes either -1 or +1, where but the denominator that is 3 the power of n when n gets larger becomes larger, so that either -1 or +1 over a very large positive number will tend to simply approach to that of this one, that's 0, so that this product will be 0. Therefore, this is the limit of this sequence. Because the limit is existing here, so that the existence of the limit will be necessary and sufficient condition for this sequence to be convergent, so that the sequence is said to be a convergent sequence. But if the limit doesn't exist, either it is positive infinity or negative infinity, or if it has more than that of one constant, so that will be the condition for this series not to be convergent, rather divergent sequence. But for this one, because the limit is existing, which is equivalent to that of 0, so that the limit that a sequence is said to be a convergent sequence. Second question is this one, and that is prove that whether the sequence that is n/2 n plus 1 when n is running from 1 to positive infinity is monotonic and bounded. Determine also it is least upper bound and greater low bound if it has. So here what we are asking here is, we have a number of questions. The first question which we are going to, or simply which we are asking here, will be checking the monotonicity property of the given sequence. Second one is we are asked just to check whether the sequence is bounded or not, and we are asked also just to find the least upper bound and the greater lower bound of the given sequence, if it has, that means. So first let us check the monotonicity property of this one. You know that a given sequence, or generally a given function, is said to be monotonic function if the function is either increasing or decreasing function on its domain. That every function or simple sequence which is either increasing or decreasing on its domain is said to be a monotonic function or monotonic sequence. So let us see whether this sequence is monotonic or increasing or decreasing or neither of these two. Therefore, here for the first property, that is monotonicity property first, and we know that um, let us take in the two consecutive general terms of this sequence, that is n, which is equal to n over to n plus 1, and the next term that is next to that of this one, which is n plus 1, which is n plus 1 over n plus 3. Then taking the ratio of these two, we have this one. That means the this one that is n plus 1 over 2 n plus 3 is this one that's simply n plus 1, and n over 2 n plus 1 is this one, which is, so that when we multiply this one, which is n plus 1, by the reciprocal of n, that is simply here, we have this product, the product of n plus 1 over 2n plus 3, which is n plus 1, multiplied by 2n plus 1 over n, which is the reciprocal of this thing, which is an. Then the product of these two could be, the product of these two fractions will be this one, that is n plus 1 over 2n plus 3, multiplied by 2n plus 1 over n. Sorry. And therefore, this product could be simply this one, that is 2n square plus n plus 1, that is n plus 1 multiplied by 2n plus 1, and 2n plus 3 multiplied by n would be 2n square plus 3n. We know that when we compare and confront the numerator of this fraction with respect to that of its denominator, we know that the numerator of this thing is larger than that of its denominator by this constant, which is 1. So that the ratio of this one could be larger than or simply greater than that of 1. That in this case, this would be a criteria for the numerator, which is in this case the an plus 1, to be larger than that of its previous, which is an. Therefore, in this case, this one, that is n, is less than that of n plus 1 for every n within the domain of the given sequence there. Therefore, this is the property for a given sequence to be an increasing sequence. Hence, the sequence is increasing if it is an increasing on its domain, so that the sequence is said to be a monotonic sequence. Monotonic because the sequence is increasing. For the second property of this thing, that's simply this point, that is, it is boundedness, because just we have proved that the sequence is monotonic, which is increasing, so that the smallest element of the sequence is its first element, that is a1, and the largest element of the given sequence must be its limit at infinity, so that for a sequence, if a sequence is monotonic, that it will have a possibility to be bounded. The sequence is bounded already from below by its first limit, first term, that is a1, because already the sequence is an increasing sequence, and if it is bounded, or simply if the limit of the given sequence is existing, so that it must be bounded from above by its limit. So as you observe here, the limit is existing, which is 1 over 2, so that this could be a real number which can bound the sequence from above, so that every term of the given sequence would be in between the first term, that is the smallest element of the possible terms of the given sequence, and this one, which is the limit of the given sequence. Therefore, every term of this one is bounded in between these two over its domain, Hence, the sequence is bounded from below by its first term, that is 1 over 3, and bounded from above by the limit of the sequence, which is 1 over 2. So that because we know that a sequence is bounded, if it is bounded from above and that of below, as we can see here, this sequence is bounded from below by this serial number and bounded from above by 1 over 2, so that it is a bounded sequence. Then, if it is bounded, the sequence will have its own least upper bound and greater lower bound. So that the greater lower bound for this one will be the smallest element, or simply the first term of the sequence, that is 1 over 3, and its least upper bound will be the limit of the given sequence, that is 1 over 2. But if the sequence was a decreasing sequence, this number that is it is greater lower bound and least upper bound will be changed. That means the greater lower bound for the an increasing sequence will becomes a least upper bound for a decreasing sequence, and the least upper bound of a decreasing sequence will becomes a greater lower bound for an increasing sequence. Anyways, but the given sequences, it is monotonic because it is increasing function. It is bounded because it is bounded both from above and that of below. And the greater lower bound for the sequence is 1 over 3, which is the first term. And the least upper bound of the sequence is 1 over 2, which is the limit of the same sequence. Okay, the next question is question number 3. And you observe here, it says determine those values of p for which the series that is the summation of 1 over n into n ln of n to the power of p when n is running from the 2 to the positive infinity is convergent. So the main idea of this one, or simply this problem, is determining the possible values of p which can make this series to be convergent, or what are the values of p which can make this series to be convergent will be the core idea of the question. So the solution will be answered by applying the integral test. But in order to apply integral test, we should first take a corresponding function on the same domain that is which is identical with the domain of the space. So the function that is f of x will be 1 over x multiplied by ln of x to the power of p over this interval, or this domain. Therefore, in order to apply the state that integral test, this function needs to be positive function over this. It must be continuous, and the function needs to be that of a decreasing function. When we see it is continuity property, we know that this one that is within this interval, there is no any value of x which can make 1 over x multiplied by ln of x, the power of p to be undefined, so that this function is clearly continuous over this interval of simply x greater than or equal to 2. Similarly, this function is positive because there is no any value of x within this interval that can make 1 over x multiplied by ln x to the power of p to be negative, so that it is both positive and negative. But for it is monotonicity or simply decreasingness, that means f is positive and continuous on due to positive infinity. So that for decreasingness, in order to check whether the sequence or simply the given function that is f of x decreasing or not, let's apply first derivative test. You know that using that first derivative test, given any function that is f of x with its domain that is d, so that this function that is f of x is said to be an increasing function on d if and only if the first derivative of this function is greater than that of d for every x which is an element of d or simply in its domain. Similarly, the function is said to be decreasing function if and only if its first derivative is always less than 0 or simply negative for every x an element of its domain or simple on the entire domain of the given function there. Therefore, let's consider this function and let's calculate its first derivative first. We know that the first derivative of this one, that's f derivative of x, is if we apply the rule of derivative for rational function, that's quotient. The derivative of the denominator, a constant that's simply 0, multiplied by this one is already 0, then minus the derivative of the denominator multiplied by the numerator. Derivative of the numerator here is the product of x and ln of x to the power of p. So that we should apply product rule. So that derivative of x that is 1 times this one, which is ln of x to the power of p, and then plus the derivative of the second or the first multiplied by the derivative of second, that is x multiplied by the derivative of ln x to the power of p will be, we should bring this one as the coefficient here, that is p into ln of x to the power of p minus 1 multiplied by, that is chain rule, derivative of ln x, which is 1 over x. So that in this case, that is this one, that simply this x can be cancelled by this one. So that what is left here is only ln of x to the power of p plus ln of x to the power of p minus 1 over the square of this function. The square of x times ln of x to the power of p whole square. Then f derivative of x could be further simplified to this thing that is simply negative, that's 0 minus, and the ln of x to the power of p plus p multiplied by ln of x to the power of p minus 1 over square of this one. We know that every term over here or simply both in the numerator and denominator is positive over the domain that is 2 to the positive infinity. But because of the existence of this negative in front of this negative positive fraction, so that this is always less than 0 or simply negative over this one. So that this will be a criteria or simply sufficient condition for the given function to be decreasing. Hence, the function that is f of x is said to be a decreasing function over this interval. So if it is increasing, and that is the function is decreasing, it is again positive and continues over the same domain that's to the positive infinity, so that a third condition for applied integral test is fulfilled. So we should proceed to the test. So let us assume that p is different from that of 1, because in the case of that of obtaining the integral, if p is exactly equal with that of 1, there will be a condition which can make the expression to be undefined. Therefore, if we assume this one, that is p is different from that of 1, we have this one that's simply this improper integral, which is equal to the limit of 2 to positive t when 1 over x multiplied by ln of x to the power of p dx. So let us integrate this one, and we'll substitute both the upper and the lower limit of integration and calculate the limit of this one, whether it is convergent or divergent, that means. Then the integral of this one is the limit, that is minus 1 over p minus 1 times ln of x to the power of p minus 1 when x is running from 2 to t. Then when we apply both the upper and the lower limit of integration for the variable x here, we have this thing that is minus 1 over p minus 1 ln of t to the power of p minus 1. That is, if we substitute this in the place of x here, we'll obtain this one. And if we substitute in the place of x here, we'll obtain this one. Notice that we have here minus 1 or simply 1 over p minus 1, 1 over p minus 1, so that we can factor out it from the limit, since it is a constant. And therefore, further, this could be, that is the determinant factor for the limit of this one could be this thing. That you have the limit 1 over ln of t to the power of p minus 1 when t approaches to that of 0. So that depending on the value of p here, this limit will have a possibility to be that of, or simply to diverge to that of positive infinity, or to converge to that of 0. Note that here, when p is greater than that of 1, so that ln of t to the power of p minus 1 will becomes very large. So in this case, 1 over a very large positive number will tend to that of 0 or will converge to 0. But when p is less than that of 1, this one that is ln of t to the power of p minus 1 will have a possibility to be a very small number. So that 1 over a very small number near to that of 0 will be a very large positive number, or simply will diverge to that of positive infinity. Therefore, the value of p, which can make this limit to converge or simply convergent, will be the possible values of p which can make the series to converge. But what will be the property of the series when p is exactly equal with that of 1? But for p is equal to 1, the original or simply the previous series will become this one. It was 1 over n into ln of n to the power of n, I mean p, when p is 1, the series looks like this. But what will be the convergent property of this series? Again, applying integral test, let the corresponding function that is f of x in this one over the same domain, so that the integral or simply this improper integral would be the limit of this one, that's simply integral to the 1 over x ln x dx. Really, this integral will be this one that is ln of ln x when x is running from 2 to t. Then when we substitute both the upper and the lower limit of integration here, the limit of ln t minus ln of ln 2, that is, this could be obtained from this one by substituting in the place of x here, and this could be obtained from this one by substituting in the place of x here. Not the constant, but the limit of ln t when t approaches that of infinity is infinity. Infinity minus this constant is infinity, so that this diverges. So that the divergence property of this improper integral is a sufficient condition for the series to diverge or simply not to be convergent at is equal to 1. Hence, the series diverges for is equal to 1. So generally, if we generalize our solution, that is simply therefore the series, that is the summation of 1 over n into ln of n to the power of p over this interval converges for p greater than 1, excluding 1, and diverges for p less than or equal to 1. So that the possible values of p, that is this p, which can make this series, that is the summation of 1 over n into ln n to the power of p, is this one, that is when p is greater than that of 1. So that for every value of p here, which is larger than that of 1, this series will converge. Okay, if you further to go back in this one, so let's proceed to the next question, which is question number 4. It says use any suitable testing method to determine whether the series, that is the summation of this fraction that is k factorial over k the power of k is convergent or divergent over this interval that's 1 to positive infinity. It's open just to use any suitable methods, that is testing method for convergence or divergence, but I think ratio test will be more suitable for this one. So what does ratio test says? We are taking this one that is n plus 1, or simply in this case ak plus 1, and general term that's simply ak. So we have to calculate the limit of the ratio of that is ak plus 1 over ak. Let, for example, ak in this one and ak plus 1 in this. Now let's calculate the limit of the ratio of this one, that is limit of ak plus 1 over ak where k tends to infinity. This one. That is this one, that's simply the term or simply the fraction. Just above this line is ak plus 1 and below this one is ak. So that simplified form of this thing could be k plus 1. That means here that's simply k plus 1 factorial over k plus 1 to the power of k plus 1 multiplied by the reciprocal of this one, which is k to the power of k over k factorial. So further, if we try to simplify this one, we have k plus 1 factorial, that is k plus 1 factorial means k plus 1 multiplied by k factorial. We have k factorial here, so that this k plus 1, k factorial will be cancelled by this one. Similarly, we have k plus 1 to the power of k plus 1 here. K plus 1 to the power of k plus 1 means k plus 1 to the power of k multiplied by k plus 1. Here we have k plus 1, so that this k plus 1 can cancel k plus 1 to the power of 1. So what's left here is, here we are left only 1 here, 1 times k to the power of k, and here we are left only k plus 1 to the power of this one, that is k. So that what we obtain here will be this one, the limit of k to the power of k over k plus 1 to the power of k. Then further, this is the equivalent with, if you take this one, that is k as a common exponent for both the numerator and the denominator, we have the limit of k over k plus 1 to the power of k. And therefore, the limit of this exponent could be, if we further simplify or simply divide both the numerator and the denominator of this fraction by k, we have k over k, which is 1, over k divided by k is again 1, plus 1 divided by k, which is 1 over k to the power of k, which is equal to 1 over this one, that is 1 plus 1 over k to the power of k, which is special limit, that is 1, e. But we know that this one, that is 1 over e, is less than that of 1, which is the criteria for the series to be convergent when it is evaluated or simply checked by ratio test. That is, if the limit of the ratio of any two general consecutive terms of the given series is existing, and if it is in between 0 and that of 1, including 0 but excluding 1, so that will be a criteria for the series to be convergent. But if it is greater than that of 1, it will be divergent. And if it is exactly equal with that of 1, no conclusion will be drawn there. So that, depending on this one, the limit is 1 over e, which is strictly less than that of 1. Therefore, the series is convergent series. Okay, let us proceed to the next one, that is question number 5. It says determine the value or the values of x for which the series, that is the summation of n factorial over n to the power of n multiplied by the power of n, x to the power of n converges. What we are asked here is, we are asked just to determine the possible values of this one, that's x, which can make this series to be convergent. That means probably the convergent property of this series will depend on this variable, that is x. So what we are asking here is, we are asked just to collect or simply find the collection of the possible values of x, which can make or that can make this series to be convergent. Therefore, the testing method or simply procedure which we are going to apply could be a generalized ratio test. What does generalized ratio test say? That if the limit of the absolute value of the ratio of this one, that's for example a n plus 1 over a n is existing and less than that of 1, so that would be a criteria for the convergent property. If it is greater than 1, it will diverge. If it is exactly equal with that of 1, no conclusion will be drawn there. That means we have to apply another tube table method just to check this convergence property. Therefore, let's we have this one, that is the general term of this series, that is n could be n factorial over n the power of n multiplied by the power of n, and the next term, that is n plus 1 is equal to n plus 1 factorial over n plus 1 to the power of n plus 1 multiplied by x to the power of n plus 1. So what would be the limit of the limit in absolute, but the ratio in absolute value, that is this one, the limit of n plus 1 over n at infinity is equal to this one, that is a matter of substitution. If you substitute this fraction in the place of n plus 1 here, and this one in the place of n here, we'll obtain this thing. Then further, it could be simplified to, if we multiply the denominator, that's simply this one, by the reciprocal of this one, we have this expression. But the simplification for this one could be, here we have n plus 1 factorial. We have also n factorial here. You know that n plus 1 factorial means n plus 1 multiplied by n factorial. We have n factorial here. So that this n factorial can cancel this one. Similarly, here we have x to the power of n plus 1, which is x to the power of n times x. We have also x to the power of n here, so that this x to the power of n can cancel x to the power of n. What we have here is only x to the power of n, 1, or simply x. And again here, we have n plus 1 to the power of n plus 1, that is n plus 1 to the power of n multiplied by n plus 1 to the power of 1. So that we have here n plus 1. This n plus 1 can cancel n plus 1 to the power of 1. So what is left here is, here we have 1 here, and we have 1x, that is x to the power of 1, n to the power of n. And here we have only n plus 1 to the power of n. So that this could be simply the same as, and this one, that is n to the power of n times x over n plus 1 to the power of n, which is equal to, because this one, that is x, doesn't have any significance role with respect to the limit of this one, because we can consider this one as a constant, then we can take out as this, like this, that is the absolute value of x times the limit of n over n plus 1 to the power of n. So what is this limit? If we again divide both the numerator and denominator by n, we have this one, that is the absolute value of x times the limit of 1, that is n over n, over 1 again here, which is this n divided by n, plus 1 over n, that is 1 divided by n to the power of n. But this is a special limit, which is the limit of 1 plus 1 over n to the power of n is e. So that we have the limit of this one, or simply this, the series, or simply this expression, the absolute value of x over this one, that is e. And therefore, because we are applying generalized ratio test, and we are arriving that the limit of this one is e, so that the convergence property of the series will depend on this limit, that is, which is r. The series will converge if this r is less than 0, less than 1, and it will diverge if this one is larger than that of 1. So um, the value of this one, that is x, which can make this expression or simply fraction to be less than that of 1, will be the possible values of this one, that is x, which can make the previous series to converge. But the value of x which can make this one to be that of greater than that of 1 will be the possible value of the variable, that is x, which can make the previous, or simply the original series, to diverge. Hence, we know that for the series to be convergent, the limit that's simply this limit, which is this one, must be less than that of 1. But for which values of x does the absolute value of x over e less than that of 1? This is simply this one, that is the absolute value of x less than that of e. That is when x is in between minus e and that of e, so that every value of x within this interval in between minus e and that of e will make the original series to converge. And therefore, the possible values of a which can make the series to converge will be the solution for this inequality, which is in between minus e and positive e. Okay, the next question will be, okay, the most probably the last question, that is, we're asked just to determine whether the series that is the summation of minus 1 to the power of n over n, when n is running from 1 to positive infinity, is absolutely convergent or conditionally convergent. We know that this is an alternating series because of the existence of the term minus 1 to the power of n, which can alternatively change the signs of the terms of the series or simply. So we know that the series is an alternating series. Let's Bn is equal to 1 over n. So Bn is decreasing and positive series on this interval because Bn is decreasing because 1 over n, when this is really a decreasing series or simply sequence, and it is positive because 1 over n is always positive within this interval, so that this series is a positive and decreasing sequence. And we know that for this alternating series to be convergent, this series needs to be positive and decreasing, and the limit of this sequence must be 0. If these two conditions are simultaneously satisfied, then this series is there to be convergent by using that of alternative series test. And the limit is 0. Again, it is positive, and that of decreasing. Therefore, this series is converges. But if even though this is convergent, it will be either absolutely convergent or conditionally convergent. We know that in addition to that of its convergency, this series is said to be, for example, absolutely convergent if the summation of the absolute value of this one converges. But if the summation of the absolute value of this one diverges, then this series is said to be convergent, but it is convergent conditionally. But let us see the summation of this absolute value. We have this one, summation of the absolute value of minus 1 to the power of n over n is equal to the summation of 1 over n. Because there is either positive 1 or minus 1, their absolute value is exactly equal with that of this one, that is 1. But we know that this series is a divergent series because it is a p series with p is equal to what? 1 is exactly 1. So it diverges. So because this is a divergent series, therefore the original series that simply this series is said to be, it converges conditionally. Converges conditionally. That means this is a justification for this one. This is divergent because it is a p series with p is equal to 1. Now from this we can conclude that the series that simply this series is a convergent series which converges conditionally. It's conditionally convergent because originally the alternating series is convergent using that of alternating series test. Since it is sequence that simply Bn is positive and decreasing, and the limit is also 0, so that this is converges by alternating series test. But the summation of the absolute value of the sequence is divergent. Therefore, this is a condition for this series to be convergent conditionally. But if the summation of its absolute value was convergent, or simply if it were converges, that the type of convergence for this series will be absolutely. But in this case, because of the divergence property of the summation of its absolute value, so that this is convergent, or it converges conditionally convergent. Okay, that is all what I have for today, or simply for this exam. Please, if you like this video, don't forget to subscribe to the channel and like, comment, and share this video with your friends. Thank you very much.